Hello, calculus fans. We just got done talking about computing the surface integral of a vector field through a parameterized surface. So naturally, now we would like to do the same thing, but in the case where the surface is given to us as a graph, z equals g of xy. Now, if we do what we did before and maybe create a parameterization where we say, well, x is x, y is y, z is g of xy, and work through what we had done before, here's what we get for the surface integral of a field f with components p, q, and r. We'll get that the surface integral of the vector field is the double integral over d of negative p dg by dx minus q dg by dy plus r. This is now just an ordinary double integral. Here, d is going to be the projection of the surface into the xy plane. And in doing so, we'll be assuming that this is an upwardly oriented surface. If for whatever reason we need to orient this thing downward, then we just take the negative of the whole thing. Okay, let's do an example. We've got a field f with components x, z, e to the y, negative x, z, e to the y, and z. And let's let s be the portion of the plane 3x plus 2y plus z equals 6 in the first octant. And we'll assume upward orientation of the surface. Okay, so if we solve for z and then represent that as our surface, then we'll say g of xy equals 6 minus 3x minus 2y. If we project the surface into the xy plane, we can do this by setting z equals 0, and we'll get this as a bounding curve, 3x plus 2y equals 6, or if you like, y equals 3 minus 3 halves x. If we project into the xy plane, then we're going to get this region in the xy plane. This is going to end up being our region of integration when we convert into a double integral. Now we're given the components of the field are x, z, e to the y, negative x, z, e to the y, and z. We know that g of xy is equal to 6 minus 3x minus 2y, so we can write down the partial derivatives of g. We'll get negative 3 and negative 2. So we'll use those in our computational formula. We're ready now to evaluate our integral. So the surface integral of the field will be negative p times dg by dx. Okay, so let's note all the pieces in here. This is negative p, this is dg by dx, minus q, so this is minus q, q already had a negative, times dg by dy plus r. Let's now write this as a double integral over the region D that we talked about. The x values will integrate from 0 to 2. The y values will integrate from 0 to 3 minus 3 halves x. And the integrand simplifies down to xze to the y plus z. Now at this point, notice that this is supposed to be a double integral in x and y. So we cannot leave these z's in place. We have to replace those with 6 minus 3x minus 3y, because that's what the value of z was along the surface that we care about. If we make that replacement, then this is what it looks like. So you'll notice that we've replaced z with 6 minus 3x minus 2y, and now this integral will be handled no problem by our computer. We get a final answer of 2/9 times 4e cubed minus 25. And if we want to think about an interpretation of this, then the field represents some kind of a flow of a fluid, and we are measuring the flow of fluid per unit time across the surface, thinking of the surface as some kind of a membrane that fluid can flow through. Okay, that's all for now.